In recent years, more and more technology has made its way into the lives of mariners. For deck officers, one of the most important innovations has been the Arpa. Within the next few years, this equipment will be mandatory in all ships over 10,000 tons. Arpa stands for Automatic Radar Plotting Aid, and that's exactly what it is, an automatic plotting aid, no more and no less. It is a computer linked to a radar set. It tracks targets, calculates their track and speed, and makes this information available to the officer of the watch. The basis of its calculations is vector analysis, the same vector analysis that is part of every deck officer's training. Given 3 positions of a target during a known time interval, the target's closest point of approach, or CPA, may be found. Knowledge of own ship's course and distance travel during the same time interval enables a vector triangle to be drawn. From this, the target's true course, speed, and aspect can be found. The Arpa's computer can carry out these calculations much faster than a human being, who also has other tasks to perform. There are many different Arpas. There are variations in the way the information is derived and displayed. However, they do all have a great deal in common in order to comply with IMO specifications. Some aspects of the equipment will be familiar to experienced radar operators. The display must be able to show relative motion, with a choice of north up, or head up, or course up. Most Arpas can also show true motion. The display must be available on at least 2 range scales, one of 3 or 4 miles, the other 12 or 16 miles. This Arpa, like many, has a large number of range scales. Next, target acquisition. Before an Arpa can begin to track, it has to acquire targets. It's always possible to do this manually, usually by circling the target with a marker, which is controlled by a joystick on the control panel. Most Arpas can also acquire targets automatically, although this is not a mandatory requirement. But however the targets are acquired, whether manually or automatically, the Arpa provides the same information on them. Firstly, the vector. Once a target has been acquired, it takes a minute or so for it to appear. This vector indicates the predicted motion of the target, based on a computation of its past movements. The display must be able to show either a relative or a true vector. Let's look at both kinds of vector on a relative motion display with north up. Own ship is in the bottom half of the screen, indicated by a heading marker. If a target represents a threat, its relative vector will point towards own ship. The length of the vector depends on the period of time it represents, and this is adjustable by the operator. Extending the relative vectors shows that provided both own ship and the target on the starboard bow maintain their present courses and speeds, a collision can be expected in about 18 minutes. With true vectors, own ship has its own vector. Potential collisions are shown by a target's vector and the own ship's vector meeting. The vectors have to actually meet to indicate a potential threat. The target on the port bow is predicted to pass astern. In this case, a very close approach is predicted, and the vector length will give the approximate time to the closest point of approach. In many systems, vector and display controls are separate. This means that there's a choice of 4 presentations with north up. Let's look at them all, showing the same traffic situation. Firstly, relative motion with relative vectors. Own ship is at the center of the screen and is steering due east, as indicated by the heading marker. Relative motion with true vectors. Own ship now has a vector. The circle on the left of the screen is the marker. It's used here to offset the display when it is switched to true motion with true vectors. And finally, true motion with relative vectors. It's up to each officer to discover which presentation he finds most useful. IMO regulations insist that there must be a visual and/or audible warning signal if any target is predicted to close within a minimum range and time set by the observer. Here, 1 nautical mile and 20 minutes has been selected. The target causing this warning must be clearly indicated on the screen. Here, a flashing triangle shows it to be to starboard of own ship at the bottom of the screen. Own ship has a flashing heading marker. The Arpa must be able to show past positions for every target being tracked. At least 4 equally time-spaced positions over a period of at least 8 minutes must be shown. Own ship does not show past positions. On this equipment, the past positions are always shown as true position plots. The same is not true of all Arpas. Finally, there must be available as a readout the following 6 pieces of information on every tracked target. Its predicted closest point of approach, or CPA. Its predicted time to the closest point of approach, or TCPA. Its calculated present bearing and range, and its calculated true track and speed. So the Arpa provides a wealth of information on a great number of targets. Close quarter warnings, vectors, past positions, as well as the readout, in this case shown on a separate panel. All this information is updated with every sweep of the antenna. Another facility designed to help officers navigate through traffic is the trial maneuver or simulation facility. It is an IMO requirement. It enables the operator to try out the effect of a proposed maneuver on all the tracked targets. Own ship is at the bottom of the screen. Altering course to starboard will avoid the target to starboard. But how will this affect the other targets? The simulation facility shows the effect of altering course 60 degrees to starboard. Provided that all targets maintain their present course and speeds, they will all pass at a distance of at least 2 miles. The IMO regulations state that target information may be presented in the form of graphics as well as vectors. Only one manufacturer offers this additional graphic display. This shows predicted areas of danger, or PADs for short. Own ship is at the center of the screen, heading southeast. The electronic bearing marker is pointing in a northerly direction. These PADs indicate areas which must be avoided to maintain a selected CPA. The greater the CPA, the larger the pad. The pads indicate potentially hazardous headings of own ship. All own ship and Arpa status information is displayed on a screen alongside the PPI. As on other systems, targets are designated by a joystick for CPA and other information. A built-in safety factor means that even if the CPA is set to 0, a target will still give a pad. A vessel going faster than own ship may have 2 pads. The way pads move is governed by complex rules. A more conventional vector display can be selected on this equipment should the operator so wish. It cannot be stressed too strongly that the Arpa is only a navigational aid, and reliance upon any one aid is potentially dangerous. Just as an officer will check a ship's position by all the means available, so the Arpa's prediction should be checked by visual sightings as well as by any other means that the officer of the watch considers necessary. Although any Arpa control panel may appear bewildering at first sight, any well-trained radar operator will be able to get useful information from it after a very short period of training. However, to be confident of knowing when he can rely on it means understanding both its capabilities and its limitations.
The only thing you can do is to look at your gate size, which you can get from pressing a synthetic.
A radar operator can think, but an ARPA cannot. It can only calculate. It's not qualified to make ship handling decisions. It can only provide information, and how accurate this is depends on the information it receives and the effectiveness of its programming. In spite of the very best efforts, it's possible for incorrect information to find its way onto the screen. One problem, perhaps the major problem, is that of speed input. Few mariners would stake their lives on the readings of any log. However, all log errors will be passed on to the ARPA and will be included in its calculations. For the ARPA simply believes all the data supplied to it. For example, let's look at a simulated log failure. The log indicates an immediate speed change from 16 knots to 2 knots. This information will be rejected by any mariner, but not by the ARPA. The ARPA display changes slowly, and the underlying cause is far from obvious to the observer. If for any reason the log becomes inoperative, then the speed must be set manually and changed manually whenever it alters, a situation which is unlikely to lead to confidence in the ARPA's calculations. Any gyro error will also be passed on to the ARPA. One method of overcoming these errors is to ground stabilize the radar, a facility available on some ARPAs. Unfortunately, this leads to other hazards. For example, here on a north-up display, own ship is heading west, having left harbour. A suitable echo from a fixed object is selected and tracked. In this case, a radio mast in the centre of the screen. Once the vector has stabilized, the ARPA is locked to it. This means that all tracking will now be based on own ship's track over the ground. So targets will now show their tracks and not their headings. As the philosophy of collision avoidance is based on headings, this is potentially dangerous. Own ship has now turned north and is indicated by the flashing heading marker. There is a strong tide running from the southwest. A target approaches from the north. The ground-stabilized ARPA suggests that this target will pass down the starboard side because it reads the tidal flow as part of the target's course and speed. In fact, this vessel is on a collision course, as the tidal flow will take own ship into its path. This is immediately apparent when the same situation is seen with the ARPA water-referenced, or as it's also called, sea-stabilized. It cannot be stressed too strongly that for collision avoidance, it's imperative to use the ARPA water-referenced. It's also good policy to check the situation with relative vectors, as these are not affected by course and speed errors other than during short updating periods. A big problem for all ARPAs is that of clutter, both rain and sea clutter. Separating weak echoes from persistent clutter can be a problem for even an experienced operator. In a gale, with only a moderate amount of rain, the ARPA may be seriously affected. In severe tropical rain, it can become virtually useless. Using a 10 centimeter radar will improve the situation. Nevertheless, it is a fact that radar, and therefore ARPA performance, can be affected by severe meteorological conditions. On occasion, waves or even clouds may be tracked. To track a target, the ARPA starts by putting a gate or window around it. How the various ARPAs differentiate between the target and the background signal varies. One problem they all share, however, is that of target swap. This may happen if a second target enters the gate. This can occur when a smaller target is eclipsed by a larger one, or when two targets simply pass close to one another. This example is speeded up 70 times and shows one ship gradually overtaking another. Changing to true vectors shows clearly that one target has lost its vector and is no longer being tracked. Target swap can never be predicted. Here's another example. One target acquires two identical vectors, while the other ceases to be tracked. The possibility of this occurring underlines the need for the bridge team to be actively involved in all available methods of potential collision assessment. Another hazard is target loss. There are many causes. A target passing into a shadow area, for example. Or as a target maneuvers, its aspect changing may mean its echo fades or goes into clutter. Another cause is the Arpa tracker swapping from a target to a wave. When the wave dissipates, the target lost alarm comes on. Target loss, like target swap, is unpredictable and emphasizes the danger of relying on one aid. All Arpas have target loss or bad echo alarms, which indicate both on the panel and on the screen. This is one of a full range of operational and malfunction alarms. All approved Arpas fulfill the IMO requirements. Many have different extra facilities. This is because each manufacturer has decided what they believe mariners want, then designed a machine and programmed it to fit these beliefs. This means that different Arpas will not necessarily do the same tasks equally well, for their manufacturers had different priorities in their design. For example, the auto acquisition facility. There are two basic types, what can be called the zonal type and the global type. Any Arpa unit will only offer one type or the other. Here, own ship is at the center of the screen, heading east. The global search area can be displayed on the screen. Its dimensions are adjustable by the operator. All targets entering this area will be acquired automatically. The other type, the zonal type, acquires targets only as they enter a specific zone. Here the zone is adjusted to cover an area ahead of own ship. A target enters the zone and is acquired, sounding an alarm. The differences between these two systems are greater than might first appear, particularly in terms of operational methods. Generally, auto acquisition has been found to be very useful in comparatively calm conditions in open sea. In restricted coastal waters or in bad weather conditions, manual acquisition is recommended. The officer of the watch will generally be told how the Arpa is set up and which targets represent a threat during the watch handover. Here, with north up, own ship is heading southwest. A target, fine on the starboard bow, is predicted to come closer than the selected CPA and TCPA limits of 1 nautical mile and 15 minutes. The length of the relative vectors is 12 minutes. The target is selected and its predicted CPA and TCPA established. The symbol seen here in the top left of the screen is a 0 speed symbol. The officer changes to true vectors and a decision to maneuver is made. Using the simulation facility, a change of course to starboard of 25 degrees is tried out. This takes care of the immediate threat without giving rise to other close-quarter situations. Changing to relative vectors checks this. The simulation is switched off and the situation checked again.
Starboard 10.
Starboard 10. 10 degrees starboard on.
Steer 260.
Steer 260. Steering 260.
260, thank you.
Once the new course is established, the officer returns to the Arpa to check the effectiveness of his maneuver. No other ships have altered course, and all targets are predicted to pass at a distance of at least 2 miles. He changes the display to true vectors. The Arpa is a navigational aid. It is useful most of the time, and on occasion it's invaluable. But it can never replace a properly trained officer. It is just a calculator. It offers speedy answers to the calculations an officer would otherwise have to do himself. It will give incorrect answers if it is supplied with incorrect data. The neat and precise way it presents the results of its calculations may trap the unwary. Remember that it is a historical display. Its predictions are based on information received some minutes previously. For officers not to be misled by it, they need to devote both time and effort to understanding its capabilities as well as its limitations. This means consulting the operator's manual and other publications. Remember your radar courses and see this film again. For the Arpa has been designed to help the officer of the watch, to relieve him of some of his workload. To make it effective, the officer must take the trouble to learn about it. Only then will it become a real aid to safer navigation at sea.